Today we're going to learn a little about the physical properties that are affected by the intermolecular forces inside a compound. So you're going to need to have out your notes, or however you take notes, and then your intermolecular forces flowchart, which is on page 12 of your Unit 5 packet. Have you ever wondered how a tree gets water all the way up to the leaves from the roots? It's got capillary action. So the inside of the tree is actually attracted to the water, and the water pulls itself up through the tree. Same thing with the paper towel. Paper towels are actually attracted to the water, so the water pulls up into it. This is why the misconception that a paper towel sucks the water up is inaccurate. The paper towel doesn't have some vacuum or suction inside of it, it's got capillary action. Because if we take a paper towel and we set it on a counter, it doesn't stick to the counter. And not all substances can be cleaned up easily with a paper towel because they don't absorb into the paper towel. Because they don't have capillary action with the paper towel itself. So it's the attractiveness between whatever material the paper towel is made out of and the water that makes those two come together, and it makes the water get pulled up into the paper towel. If you put water into a graduated cylinder, whether it's glass or plastic, the water is attracted to the container. It has a high capillarity. So the water forms that meniscus, where it's up higher on the sides. If you do this with another substance, say mercury, mercury will actually go the opposite direction. You'll get a bubble, because the mercury is not attracted to the inside of the container. Well, mercury has a really low capillarity. It's not going to pull up on its own. You have to push it up. Water or like alcohol will form so like rubbing alcohol, for example, is also attracted to its container, so it also has a capillarity, but it's not as high as the water's capillarity because water is not nearly as polar. So rubbing alcohol will have a lower meniscus, so it'll have a smaller gap here because water doesn't have as high of a capillarity, so it's not as attracted to the outside of the container. So next we're going to talk about boiling point. And boiling point is how readily a substance boils, or how much energy we have to put in to get it to boil. And when we talk about boiling point, people get bogged down with the actual temperature at which something boils, which is true, but it's how much energy has actually gone into the substance, because the energy breaks the bonds in the substance, and it breaks those intermolecular forces. So the stronger the intermolecular forces inside something, the higher the boiling point is going to be, because the stronger that those molecules are going to be held together. So oil here has a long carbon chain, which we talked about earlier with capillarity, and then it also has hydrogen bonding to hold the molecules together. So the oil isn't breaking apart as easily as the water does, which just has hydrogen bonding in it. So the stronger the IMFs, the higher the boiling point is going to be, because we have to put in more energy to get the molecules to rip apart. This would be similar to freezing point or melting point, where melting point's talking about going from a solid to a liquid. So in order to get ice to melt, we have to put energy in. The stronger the attractions within a frozen solid or within a solid, the more energy you have to put in to get them to melt. So metallic compounds, like if you have a chunk of iron, for example, you have to put a lot of energy in order to get that to break down and become a liquid, in order to get that to melt, because the intermolecular forces inside metallic compounds are so high. Similarly, water is going to take less energy because it's got weaker intermolecular forces than a chunk of metal would.
Hold on.
Okay, so the next physical property that we're going to talk about is volatility. And volatility is how quickly the substance can vaporize or evaporate. So this actually goes back to that like boiling point and melting point physical property that we talked about earlier. So it's all about the strength of the forces between the molecules. So the stronger the force is, the harder it's going to be to break those forces. Therefore, it won't evaporate, which is changing from a liquid, right, to a solid, or a liquid to a gas, excuse me. So it won't evaporate as quick if it has stronger forces between them. The weaker the forces, the quicker it will evaporate or vaporize, and therefore it would have a higher volatility. So for example, if I were to use water and like acetone, so like fingernail polish remover, or even alcohol, the water has a little bit stronger bonds because it's all hydrogen bonding, and the alcohol or the acetone has kind of a mixture of dipole-dipole forces and hydrogen bonding. So those dipole-dipole forces will actually break apart because they, have a lower boiling point and therefore will vaporize quicker. So they would have a higher volatility than hydrogen bonding. So as you go up in strength of the forces, it will have a lower volatility, and as you go down, so London dispersion and dipole-dipole, those would have weaker forces, therefore a higher volatility.
All right, so now we're going to talk about surface tension. And if we take some water and we drop it onto this penny, we can get the water to bead up and be in a kind of a bubble. It doesn't just fall off the penny altogether. If you can zoom in and see that a little bit. And we can get a lot of water to stay on top of this penny, and it actually starts to bubble over the top of the penny without going over. Whereas this acetone won't even stay in the pipette long enough. It just squirts right out, and we get all of the acetone laying flat instead of bubbled up on top of the penny. So the reason this happens is what's called surface tension. Surface tension is how the molecules on the top of a liquid actually form kind of a skin. And so what ends up happening is intermolecular forces are between all molecules in the area and that specific molecule that we're talking about. So for example, this molecule of water right here in our beaker has to attract to every single molecule around it. But this molecule up here has less things that it has to attract to, so less molecules it has to attract to. So again, this one down here is going to bond to here, it's going to have some hydrogen bonding there. If this is water, we're going to get some hydrogen bonding all around it. Whereas up here at the top, this guy only has to connect to the ones on the top, and he's got all this extra energy. Each molecule has a certain amount of pull they have because of their partial positive or partial negative. So if that pull is distributed out to more molecules down here, then it can't hold on as strong. Whereas up here at the top, this one molecule can hold on really strong to everything around it. So we get a skin across the top. This is why the basilisk lizard is actually able to run across the top of the water, is because he's able to fight the surface tension. Or you can actually float a paperclip across a beaker of water because of the surface tension on the water. So the stronger the IMFs, the more surface tension you're going to get. So hydrogen bonding is going to have a much stronger surface tension than dipole-dipole. But this really only applies to those liquid compounds.
Okay, so the next one we're going to talk about is solubility. And solubility is the ability of a molecule to dissolve in another molecule, or a substance to dissolve in another substance. And we use the phrase like dissolves like. So what that means is if you have a substance that is polar, for example, it will dissolve in another polar sample. So here I have water and I have hydrochloric acid. And when I pour them together, you can clearly see that they are mixed. They're soluble. You can't actually determine what is hydrochloric acid and which one is water. So this would be a soluble mixture of the two. Okay. The other reason, or the other ones that are soluble would be non-polar and non-polar molecules. So if you have something that's non-polar, it will dissolve or be soluble in another substance that is non-polar. And then if you have a polar molecule and a ionic compound, the ionic compound will also dissolve in the polar molecule. So for example, salt will dissolve in water. So water is the polar molecule and salt is the ionic compound. So those are also soluble. Some examples of things that are not soluble would be if you mixed a polar molecule and a non-polar molecule. So an example of this that I have is water and oil. So you guys have probably seen this before. So when you mix the two together, they actually separate out, okay? And that's because they are not the same. So one is polar and then the oil has some non-polar ends to it, okay? Here's another example that you might see around the holiday. So a snow globe, right? So the little flakes that are inside of the snow globe are not the same. So like dissolves like, these are not the same as the water or the fluid that's in here. So this would be an insoluble substance. Okay, so the next physical property that we're going to talk about is conductivity. So conductivity varies depending on which IMF you're looking at. And it's all about what the electrons do and the charge that can go through those electrons. So if you guys remember from the IMFs when we did the presentations with the expert groups, the metallic group was talking about how we have this sea of electrons. Okay, so when you have all these metals that get put together and those electrons are kind of free roaming around, if one of them has a charge, it actually can transfer that charge to all those electrons, okay, and they will all shift together and carry that charge through the metals. When it carries that charge through the metals, it actually is a conductor, okay, of that heat or that electricity that is able to flow through that metallic bond or those metallic forces. Okay, so the sea of electrons are what allow a metallic force to be conductive, so travel heat or electricity through. That's why when we are cooking, okay, if we want something to heat up, oftentimes we will use metal pots, metal pans, that kind of thing. The other one that conducts electricity is macroionic, and it actually conducts a little bit less than metallic, and the reason for that is because of dissociation of the ions. Okay, so what happens whenever you put a macroionic compound into into water, let's say, it will separate, and you will have a sodium ion and you will have a chlorine ion. Okay, those charges, that positive and that negative charge, when they are dissolved in, remember we talked about solubility, so when they're dissolved in that water, will allow for heat or electricity to be able to travel through that solution. Okay, that's why when you are like swimming, and they always say don't swim when it's lightning out, or be careful with like power lines or electricity around water. It's because it's not pure water. It has ions in it, such as sodium chloride or whatnot, that will dissociate and then allow that charge to travel through. Okay, so going off of that, if you have a pure like H2O molecule, so you have hydrogen bonding, that actually won't conduct electricity. And then macrocovalent, we actually use those a lot for cooking too, because they are very, very poor conductors of electricity and heat. So if you have like a clay or glass pan or whatever, oftentimes it will cool faster or not heat up as fast, so you can take it out of the oven because they are poor conductors of heat and electricity. So macrocovalent, dipole, and hydrogen bonding would be poor conductors of heat and electricity. Now there is one special circumstance with dipole. Oftentimes when you have a dipole, it will dissociate water. So like, for example, hydrochloric acid, HCl. When you put that in, it'll do the same thing as macroionic. It will dissociate, but it is very weak compared to the macroionic. So oftentimes you might get a reading that is conductive, but it'll be a lot less than metallic and ionic.
So at this point, we've talked about all of your intermolecular forces and how the physical properties apply to your intermolecular forces. So we talked about solubility and how like dissolves like. We talked about surface tension and that skin on top of the like a beaker of water and how you can float a paper clip across it, which we'll try in class. And then we talked about conductivity very briefly at the end there, a little bit about boiling point and adding heat and volatility and evaporation, and then even a little on capillarity. So if any of these topics are confusing to you, feel free to either use the additional resources on the page, go back and watch this video again, or you can always check in your book. If you're feeling ready, your formative password is snow globes. So if you go on to our Unit 5 page and you take the formative, the password is not case sensitive and there is not a space. Good luck.